Above us tonight, as it has been for over 4 billion years, hangs the moon. It moves through the darkness at a distance of about 238,855 miles from where you rest right now. That distance never changes by more than 31,000 miles throughout its entire orbit, a variation so gradual you would never perceive it in a single night or even a single year of watching. The moon completes one orbit around Earth every 27.32 days. During that time, it also rotates exactly once on its axis, which is why we always see the same face looking down at us. This synchronization happens slowly, over hundreds of millions of years, as Earth's gravity gently tugged on the moon's slight bulges until its rotation matched its orbit perfectly. The process was so gradual that if you could have watched from the beginning, you would have seen no change within a human lifetime or even within 1,000 human lifetimes. Tonight, we're going to explore the moon together. Not the moon of myths or imagination, but the actual moon, the one that astronauts have walked upon, the one that spacecraft have photographed in extraordinary detail, the one that scientists have measured and studied with instruments sensitive enough to detect the faintest whisper of hydrogen atoms drifting above its surface. We'll move through its history, its structure, its influence on our world, and the quiet facts that make it one of the most thoroughly understood objects beyond Earth. This will be a long journey, measured not in the speed of thought, but in the patience of observation. We won't rush through facts or pile wonder upon wonder. Instead, we'll let each aspect of the moon settle into understanding before moving to the next. You don't need to remember everything. You don't need to stay alert or focused. You can simply let the information wash over you, like moonlight itself, gentle and constant and requiring nothing from you in return. The moon has a diameter of 2,159.14 miles. That makes it slightly more than 1/4 the width of Earth. If you could somehow place them side by side, you would fit about 4 moons across Earth's equator with a small gap remaining. In terms of volume, you could fit 49 moons inside Earth's volume. But the moon is less dense than our planet, composed of lighter materials, so its mass is only 1.23% of Earth's mass. Even though it's substantial enough to qualify as the 5th largest moon in our entire solar system, it remains, in cosmic terms, a lightweight companion. The surface area of the moon measures about 14,600,000 square miles. That's roughly the same as the combined land area of Africa, which spans about 11,700,000 square miles, or the combined area of Asia and Europe's smaller nations. Every crater, every mountain, every flat plain of ancient lava exists within that measured space, mapped now with precision down to features smaller than a house. From Earth, the moon appears to be about half a degree across in our sky, the same angular size as the sun. This is coincidence, not design. The sun is about 400 times wider than the moon, but it's also about 400 times farther away. And these ratios happen to align almost perfectly from our viewpoint. This alignment allows for total solar eclipses, where the moon slides precisely in front of the sun and blocks it completely, revealing the sun's outer atmosphere in a display that lasts only a few minutes before the geometry shifts again. But we're getting ahead of ourselves. Before we can understand what the moon does, we should understand what the moon is. And to understand what it is, we need to go back to how it formed, back to an event that happened so long ago that the numbers themselves become difficult to imagine. The moon formed approximately 4.51 billion years ago. To put that in perspective, if you compress the entire history of the moon into a single 24-hour day, humans would have existed for about the last 3 seconds before midnight. Written language would have appeared in the final third of the final second. Everything we call recorded history occupies less time than a single heartbeat in the moon's existence. The most widely accepted explanation for how the moon formed is called the giant impact hypothesis. According to this model, during the early formation of our solar system, when Earth was still molten and relatively young, another planet-sized body collided with it. This impactor, sometimes called Theia after a Greek Titaness, was roughly the size of Mars, with a diameter of about 4,200 miles. The collision happened at an angle, not head-on, and occurred at a speed of about 22,000 miles per hour. The impact released energy equivalent to billions of nuclear weapons detonating simultaneously. But this comparison, while technically accurate, doesn't capture the actual nature of what happened. This wasn't an explosion in the usual sense. It was a merging of molten rock on a planetary scale, a collision so massive that both Earth and the impactor partially vaporized and mixed together in the heat. Temperatures at the impact site may have exceeded 10,000 degrees Fahrenheit, hot enough to turn rock into gas. The debris from this collision, a mixture of vaporized and molten material from both Earth and Theia, was thrown into orbit around the young Earth. Most of Theia's iron core merged with Earth's core, sinking down through the molten mantle. But the lighter, rocky material, the silicates and oxides that make up planetary crusts and mantles, was ejected into a disk of orbiting debris. This disk extended perhaps 13,000 to 23,000 miles from Earth's surface, a ring of molten droplets and vapor slowly cooling in the darkness of space. Within this disk, gravity began to pull material together. Small clumps attracted other clumps, growing larger through countless small collisions. The process was efficient. Within a period estimated at between 10 million and 200 million years, most of the disk material had either fallen back to Earth, escaped into space, or gathered into a single body, the Moon. On geological timescales, this is remarkably fast. The Moon essentially assembled itself in less time than it would later take for life to evolve from single-celled organisms into complex animals on Earth. When the Moon first formed, it was much closer to Earth than it is now. Initial estimates place it at a distance of somewhere between 9,315 miles to 15,530 miles away. From Earth's surface, if you could have stood on the molten rock and looked up through an atmosphere, completely unlike today's, you would have seen the Moon spanning perhaps 10 to 20 degrees of the sky, 20 to 40 times larger in apparent size than it appears now. It would have been an overwhelming presence, moving visibly across the sky, completing an orbit not in 27 days, but in perhaps 6 hours. The young Moon was also molten. The energy from all those colliding fragments as it assembled, combined with tidal heating from Earth's gravity, acting on its distorted shape, kept much of the interior liquid. The entire outer layer, extending down to a depth that may have reached 43 to 93 miles, existed as an ocean of molten rock. Scientists call this the lunar magma ocean. This ocean didn't remain liquid forever. Without plate tectonics to recycle heat, without a thick atmosphere to trap warmth, the surface of this magma ocean began to cool and solidify. Lighter minerals, particularly plagioclase feldspar, floated to the top like cream rising in milk. Denser minerals like olivine and pyroxene sank toward the interior. This process of separation, called magmatic differentiation, took somewhere between 10 million and 200 million years. The result was a layered moon, a crust of light-colored rock floating on a mantle of denser minerals, with a small core of iron and nickel at the very center. The lunar crust that formed from this cooling is between 20 and 93 miles thick. It's thicker on the far side of the moon than on the near side, though scientists aren't entirely certain why. The most probable explanation involves the tidal effects of Earth's gravity acting on the still-forming moon, but this remains an active area of research, with new data from recent lunar missions still being analyzed. As the surface solidified, the moon began to look more like the world we know today, though it was about to undergo another major transformation. Between about 4.1 and 3.8 billion years, ago, the inner solar system experienced what scientists call the late heavy bombardment. During this period, the moon, along with Earth and the other inner planets, was struck by an enormous number of asteroids and comets. The rate of impacts during this time was perhaps 20,000 times higher than the impact rate today. These impacts created most of the large craters we see on the moon. The biggest impacts excavated enormous basins, some of them more than 1,200 miles across and several miles deep. The force of these impacts shattered and melted the lunar crust, fracturing it to great depths and creating weaknesses that would later allow lava to reach the surface. After the late heavy bombardment ended, roughly 3.8 billion years ago, volcanic activity began to fill some of the largest impact basins with lava. This wasn't explosive volcanism like we see on Earth. The moon's low gravity and lack of atmosphere meant that lava simply welled up from fractures in the crust and flowed across the surface, layer after layer, gradually filling the low-lying basins. This process continued for over 1 billion years, with the last volcanic flows occurring around 1 billion years ago, though some research suggests isolated volcanic activity may have continued to as recently as 100 million years ago, or even more recently. By about 3 billion years ago, the moon had essentially reached its current geological state. Its interior had cooled enough that widespread volcanic activity ceased. Its surface, heavily cratered and partially resurfaced by ancient lava flows, began the long, slow process of accumulation that continues today, as micrometeorites, tiny particles smaller than grains of sand, constantly rain down and gradually build up a layer of pulverized rock called regolith. This entire history, from violent formation to gradual cooling to steady accumulation, is written in the rocks and soil of the moon. Unlike Earth, where plate tectonics constantly recycles the surface, and where erosion from wind and water wears away geological records, the moon preserves its history with extraordinary fidelity. A footprint left in lunar soil could remain visible for millions of years, protected by the absence of wind and water. A crater formed 3 billion years ago looks almost the same today as it did when it was fresh. The moon is not a perfect sphere. It's slightly egg-shaped with the long axis pointed toward Earth. This distortion is subtle, only about 1 mile in the difference between the longest and shortest diameters, but it's measurable and permanent. Earth's gravity pulled the moon into this shape when its interior was still partly molten, and it has remained this way ever since. The moon's mass is precisely known: 134 septillion, 570 sextillion pounds, or using scientific notation, about 7.346 times 10 to the power of 22 kilograms. This mass is spread through a volume of 5.003 times 10 to the power of 9 cubic miles. The resulting average density is about 210 pounds per cubic foot, or 3.34 grams per cubic centimeter. This is significantly less dense than Earth, which has an average density of about 345 pounds per cubic foot. The difference tells us that the moon has a smaller iron core relative to its size compared to Earth, and that it's composed primarily of lighter, rocky materials. The moon's core is relatively small. The liquid outer core has a radius of about 205 miles, while the solid inner core has a radius of about 150 miles. Combined, the core represents only about 1 to 2% of the Moon's total mass compared to Earth's core, which makes up about 32% of Earth's mass. This small core generates almost no magnetic field, certainly nothing like Earth's protective magnetic bubble. The Moon's surface magnetic field is less than 1/100th the strength of Earth's field, and what little magnetism exists comes primarily from ancient rocks that were magnetized billions of years ago when the Moon may have had a stronger field. The surface of the Moon experiences temperature extremes unlike anything on Earth. In direct sunlight, surface temperatures can reach about 260 degrees Fahrenheit. In darkness, temperatures plummet to about -280 degrees Fahrenheit. This range of 540 degrees exceeds any temperature variation found naturally on Earth. The extremes exist because the Moon has essentially no atmosphere to distribute heat. On Earth, air and water transport warmth from hot regions to cold regions, moderating temperatures. On the Moon, each patch of ground heats or cools based solely on whether sunlight is hitting it at that moment. The transition between these extremes doesn't happen instantly. The lunar surface heats and cools relatively slowly because the regolith, that layer of pulverized rock and dust, acts as an insulator. Even though individual particles can heat up quickly, the spaces between particles contain vacuum, which prevents heat from conducting downward efficiently. A thermometer placed 1 meter below the surface would register a nearly constant temperature of about -4 degrees Fahrenheit, regardless of whether the surface above was baking in sunlight or frozen in darkness. The Moon's low gravity creates an environment profoundly different from Earth's. The surface gravity is about 1/6 of Earth's, or more precisely, 1.62 meters per second squared compared to Earth's 9.81 meters per second squared. This means that if you weigh 180 pounds on Earth, you would weigh about 30 pounds on the Moon. Your mass wouldn't change, but the force pulling you downward would be much weaker. This low gravity has shaped the Moon's landscape in distinctive ways. On Earth, mountains have a practical height limit because the weight of rock eventually becomes too great for the base to support. On the Moon, with 1/6 the gravity, mountains can rise much higher before structural limits are reached. The Månshöjdens, the Moon's tallest mountain, rises about 15,090 feet above the surrounding plains, roughly the height of the tallest mountains on Earth, but built from rock that experiences far less crushing weight at its base. The regolith that covers the Moon's surface extends downward to varying depths, typically between about 10 and 65 feet. This layer consists of fragments ranging from microscopic dust particles to rocks several feet across, all thoroughly mixed by billions of years of meteorite impacts. The finest dust particles are sharp and angular because they've never been rounded by wind or water. Under a microscope, they look like tiny shards of broken glass, and indeed, many of them are exactly that. Impact-melted rock that solidified into glass and then shattered. This regolith has some unusual properties. It compresses under weight, becoming more compact, but it also clings together slightly due to the sharp, interlocking shapes of the particles. Apollo astronauts found that their boot prints compressed the soil to a depth of a fraction of an inch, but left sharp, well-defined edges because the disturbed soil didn't flow or settle the way sand would on Earth. They also found that the dust clung to their spacesuits through electrostatic forces, coating everything it touched with a fine gray powder that smelled, several astronauts reported, somewhat like spent gunpowder. The composition of the lunar surface varies from place to place, but overall it consists primarily of oxygen, silicon, aluminum, calcium, iron, magnesium, and titanium. These elements combine to form minerals, mainly plagioclase feldspar in the bright highland regions and pyroxene and olivine in the darker Maria. Small amounts of other elements exist as trace components, including potassium, phosphorus, and various rare earth elements. One thing notably absent from the Moon's surface is water, at least in the regions illuminated by sunlight. The combination of intense solar radiation, vacuum conditions, and the solar wind, a stream of charged particles flowing out from the sun, removes any water molecules that might appear on the sunlit surface. For most of the Moon's mapped surface, the amount of water present is measured in parts per million, barely detectable even with sensitive instruments. But the Moon is not entirely dry. In permanently shadowed craters near the poles, where sunlight never reaches and temperatures remain below -298 degrees Fahrenheit, water ice exists, protected from the destructive effects of solar radiation. The amount of ice in these cold traps is uncertain, but potentially substantial. Estimates range from tens of millions to hundreds of millions of tons, existing as pure ice deposits, or more likely, as ice crystals mixed with regolith. We'll explore this in more detail later, but for now, it's enough to know that the Moon holds water in specific, protected locations, a discovery that has reshaped our understanding of lunar resources. The Moon has no global magnetic field, as mentioned, but it does have localized magnetic anomalies, regions where the surface rocks produce measurable magnetic fields stronger than the surroundings. These anomalies exist primarily on the side of the Moon, opposite the largest impact basins. The most likely explanation involves the giant impacts that created those basins. When an enormous object slams into the Moon, it sends shock waves through the interior. These waves can converge on the opposite side of the Moon, churning and heating the rocks there. If this happened while the Moon still had a significant magnetic field, the rocks cooling in that field could have become permanently magnetized, preserving a record of the ancient magnetic environment. The Moon experiences moonquakes, though they're very different from earthquakes. Deep moonquakes occur about 434 miles below the surface, likely caused by tidal stresses as Earth's gravity flexes the Moon's interior slightly during each orbit. These deep quakes are small, typically registering less than magnitude 3, and they occur in clusters at specific depths, suggesting they're linked to particular weak zones in the mantle. Shallow moonquakes, occurring at depths less than 124 miles, are much rarer but can be stronger, occasionally reaching magnitude 5 or above. These shallow quakes might be related to the slow cooling and contraction of the Moon's interior, causing the crust to crack and shift slightly. Thermal moonquakes occur as the surface heats up during the lunar day and contracts during the lunar night, producing small vibrations as rocks expand and contract. Finally, meteorite impact moonquakes occur when objects strike the surface, sending vibrations through the ground. All of these moonquakes are detectable but generally weak. The Moon doesn't have the kind of vigorous seismic activity that Earth experiences. Seismic waves also propagate differently on the Moon. Because the surface layer is so fractured and broken, seismic waves scatter and lose energy quickly near the surface. But in the deeper, more solid interior, waves can travel efficiently. Moonquakes detected by seismometers placed by Apollo astronauts would ring for up to an hour, the vibrations gradually fading away in an environment with no water or atmosphere to absorb them. On Earth, most earthquake vibrations cease within a minute or two, because the energy dissipates into the surrounding materials. When you look at the Moon with the naked eye, you see light and dark regions. The bright areas are called highlands, and the dark areas are called Maria, a Latin word meaning seas. Early telescopic observers thought these dark, smooth regions might be bodies of water, and the name persisted even after it became clear they were nothing of the sort. The Maria cover about 16% of the Moon's near side, but only about 2.5% of the far side. This asymmetry is one of the Moon's most striking features. The near side, the face we always see, has large expanses of dark lava plains. The far side is almost entirely bright highlands, heavily cratered and ancient. The Maria formed when lava welled up from the Moon's interior and filled large impact basins. These weren't continuous eruptions in the sense of a volcanic mountain constantly spewing lava. Instead, lava flowed through fractures in the basin floors, spreading out in thin sheets that gradually accumulated over millions of years. Individual lava flows on the Moon were probably similar to basaltic lava flows on Earth, relatively fluid, slow-moving rivers of molten rock that could travel many miles from their source before cooling and solidifying. The lava that formed the Maria is basalt, a dark volcanic rock rich in iron and magnesium. Analysis of lunar samples shows that mere basalts contain about 18 to 22% iron oxide and about 5 to 14% magnesium oxide, higher concentrations than most Earth basalts. This gives them their dark color and relatively high density compared to the highland rocks. Different Maria have slightly different compositions and ages. Mare Tranquillitatis, the Sea of Tranquility, where Apollo 11 landed, contains basalts that are approximately 3.5 to 3.8 billion years old. Mare Imbrium, the Sea of Rains, one of the largest Maria, was filled with lava between 3.1 and 3.8 billion years ago in multiple episodes. Some small patches of Mare basalt are significantly younger. Samples from the Apollo 12 landing site showed ages as young as about 3.2 billion years, and crater counting studies suggest some localized lava flows might be as recent as 1 billion years old. Each mare has its own name, usually fanciful, and often retaining the original Latin. Mare Serenitatis means Sea of Serenity. Mare Nectaris means Sea of Nectar. Mare Frigoris means Sea of Cold. Oceanus Procellarum, the Ocean of Storms, is the largest dark plain, stretching about 1,500 miles across and covering an area larger than India. Despite its dramatic name, it's as dry and airless as every other part of the Moon. The highlands contrast sharply with the Maria. They're bright, heavily cratered, and ancient. The rocks here are primarily anorthosite, a light-colored rock composed mostly of plagioclase feldspar. This is the material that floated to the top of the lunar magma ocean as it cooled, forming the Moon's original crust. Highland rocks are typically 4.4 to 4.5 billion years old, representing the Moon's earliest solid surface. The difference in color between Maria and highlands isn't dramatic when you're standing on the Moon. Both are various shades of gray, with the Maria being darker gray and the highlands lighter gray. The contrast looks more pronounced from Earth because we're seeing them from a distance, where even subtle differences in reflectivity become apparent. The highlands reflect about 12 to 18% of the sunlight that hits them, while the Maria reflect only about 7 to 10%. Neither surface is particularly reflective. For comparison, fresh snow reflects about 80 to 90% of sunlight. The Moon is actually quite dark, roughly the same reflectivity as worn asphalt. Within the Maria, you can sometimes see subtle variations in tone and color. These variations correspond to different lava flows with slightly different compositions, or ages. Some areas have slightly higher concentrations of titanium, which makes them appear a bit darker or, under certain lighting conditions, slightly bluish. Other areas have lower titanium content and appear lighter or more orange. These color differences are very subtle, generally requiring careful photographic analysis to detect, but they provide clues about the sequence of volcanic eruptions that filled each basin. The Maria are relatively smooth compared to the highlands, but they're not perfectly flat. They contain wrinkle ridges, long sinuous ridges that form when the lava surface buckled and folded as it cooled and contracted. Some wrinkle ridges stretch for hundreds of miles, rising perhaps a few hundred to a few thousand feet above the surrounding plain. The Maria also contain rills, which are channel-like features. Some rills are collapsed lava tubes, underground channels where lava once flowed. Others are graben, valleys formed when blocks of crust drop down, between parallel faults. A few are sinuous rills, meandering channels that might have been carved by flowing lava or possibly by flowing gas during volcanic activity. One particularly interesting feature found in some Maria is called a volcanic dome. These are low, broad bumps on the surface, typically several miles across and a few hundred feet high. They probably formed when thick, viscous lava piled up around a vent rather than flowing away. The Moon has several dozen confirmed volcanic domes, mostly in Oceanus Procellarum and Mare Tranquillitatis. Their subtle features, best seen when the sun is at a low angle and casts long shadows that highlight small elevation changes. The highlands are sometimes called the terrae, Latin for lands. They represent the Moon's original surface, battered by billions of years of impacts. Almost every square foot of the highlands shows the scars of meteorite strikes, craters within craters, overlapping rims, scattered blocks of ejected rock, and rays of bright material spreading out from more recent impacts. Walking through the highlands would be dramatically different from walking across a mare. Instead of a relatively smooth plain, you'd navigate a chaotic landscape of crater rims, boulder fields, and rough terrain. The soil would be similar in texture to mare regolith, fine-grained and dusty, but lighter in color and containing different minerals. Analysis of highland samples shows they're composed mostly of calcium-rich plagioclase feldspar, typically about 90 to 98% pure in some rocks, making them almost monomineralic, a single mineral forming nearly the entire rock. The highland mare boundary is usually sharp. In many places you can see exactly where the lava stopped, pooled against the rim of the basin it was filling. Some isolated highland peaks rise from mare surfaces like islands from a sea, which is exactly what they are. Mountains of ancient highland material that were tall enough to protrude above the lava that flooded the basin around them. Both the Maria and highlands are covered with impact craters of all sizes, though the highlands have far more, especially small craters. On average, the highlands have about 10 times more craters per unit area than the Maria, simply because the highlands are older and have been exposed to impacts for a longer period of time. The Maria, being younger, show fewer impacts, only those that occurred after the lava flows solidified. Impact craters are the Moon's most abundant landform. They range in size from microscopic pits a fraction of an inch across to enormous basins hundreds of miles in diameter. The largest confirmed impact structure on the Moon is the South Pole Aitken Basin, which stretches about 1,600 miles across and reaches depths of about 5 miles below the surrounding terrain. It's one of the largest impact structures in the entire solar system. Craters form when objects from space strike the Moon's surface. The process is violent but brief. When an asteroid or comet hits the Moon, it's typically traveling between about 11,000 and 160,000 miles per hour. At these speeds, the impactor has enormous kinetic energy. Upon striking the surface, this energy converts almost instantaneously into heat and shock waves. The impactor and an equal volume of lunar surface material vaporize completely. The shock wave expands outward, pulverizing rock and excavating a bowl-shaped depression. For small impacts, the process ends there, leaving a simple, bowl-shaped crater. But for larger impacts involving more energy, the sequence becomes more complex. After the initial excavation, the crater floor rebounds, bouncing back upward as the compressed rock beneath decompresses. This creates a central peak, or, in the largest craters, a peak ring, a circular mountain range around the crater's center. The crater walls, unstable and oversteepened, collapse inward, forming terraces. The final result is a complex crater with a flat floor, terraced walls, and central peaks. The transition from simple to complex craters occurs at different sizes on different worlds, depending on gravity. On the Moon, craters smaller than about 9 to 12 miles in diameter are typically simple. Larger craters are complex. The size threshold depends on how quickly the shocked rock can flow and adjust after impact, which in turn depends on gravity's strength. On Earth, with higher gravity, the transition occurs at smaller sizes, around 2 to 2.5 miles for craters in crystalline rock. Many lunar craters have names, usually honoring scientists, astronomers, and other notable figures. Copernicus crater, one of the most prominent features visible from Earth, measures about 58 miles across and reaches a depth of about 2.4 miles from rim to floor. Its central peaks rise about 2,400 feet above the floor. Tycho crater, about 53 miles across, is famous for its bright rays of ejected material that extend across much of the Moon's southern hemisphere. These rays consist of fresh, bright material thrown out by the impact, and they remain visible because the airless environment prevents them from darkening quickly. Over time, exposure to the solar wind and micrometeorite bombardment darkens lunar rocks, but this process is extremely slow. Tycho's rays remain bright even though the crater is about 108 million years old. Some craters are ancient beyond easy comprehension. The South Pole Aitken Basin formed about 4.3 billion years ago during the earliest period of lunar bombardment. If you could somehow stand at the bottom of this basin when it was fresh, you would look up at walls rising miles overhead, still glowing red from the heat of impact, with molten rock pooling on the floor and blocks of crust the size of mountains sliding down unstable slopes. Now, 4 billion years later, the basin has been filled partially with later debris and modified by countless subsequent impacts, but its basic structure remains, a permanent scar recording one of the most energetic events in the Moon's history. Crater counting is one of the primary methods scientists use to determine the ages of lunar surfaces. The principle is straightforward. Older surfaces have more craters because they've been exposed to impacts for longer periods. By counting the number of craters of various sizes in a given area and comparing this to surfaces of known age, scientists can estimate the age of any lunar surface with reasonable accuracy. This technique works because the rate of impacts has changed in a predictable way over time. During the late heavy bombardment, about 4.1 to 3.8 billion years ago, the impact rate was very high. After that, the rate dropped sharply and has declined gradually ever since. Surfaces that solidified before the late heavy bombardment show an extremely high crater density. Surfaces that formed after show progressively fewer craters the younger they are. The Apollo missions brought back samples that could be dated precisely using radiometric techniques, measuring the decay of radioactive elements within the rocks. These samples came from surfaces where craters had been counted, allowing scientists to calibrate the crater counting technique. Now, even without samples, a careful crater count can provide age estimates accurate to within a few 100 million years. Not all craters are the same age or preserve the same level of detail. Fresh craters have sharp rims, well-defined ejector blankets, and bright rays. Ancient craters are degraded, their rims worn down by billions of years of subsequent impacts, their floors filled with debris, their rays long since faded to match the surrounding terrain. The degree of degradation provides another way to estimate relative age. Some craters overlap, with newer craters superimposed on older ones. When this happens, the sequence is clear. The crater that cuts through another must be younger. By mapping these relationships across the Moon, scientists have constructed a detailed geological history, a sequence of events spanning billions of years, all without visiting most of the areas in question. Certain craters have features that tell specific stories. Some have dark halos of excavated mare basalt, indicating the impact punched through a thin layer of lighter regolith to reveal the dark rock beneath. Others have bright halos, suggesting they excavated through dark material to reach lighter highlands. A few craters show asymmetric ejecta patterns, with material thrown farther in one direction than others, indicating the impactor came in at a very low angle, almost grazing the surface. Boulder tracks are another fascinating feature. In some craters, especially those on slopes, you can see trails where large rocks rolled downhill, leaving tracks in the regolith as they bounced and tumbled. These trails can extend for hundreds of yards, perfectly preserved because there's no wind to erase them. Eventually, over millions of years, micrometeorite bombardment will obliterate the tracks, but for now, they remain as fresh as if the boulder rolled yesterday. The permanently shadowed craters near the lunar poles are especially intriguing. Because the Moon's axis is tilted only about 1.54 degrees relative to the plane of its orbit around the Sun always stays near the horizon at the poles. Deep craters at these latitudes can have floors that never receive direct sunlight. Temperatures in these permanently shadowed regions remain below -298 degrees Fahrenheit, cold enough that water ice, if present, can remain stable for billions of years. Recent spacecraft observations have confirmed that water ice does indeed exist in some of these craters. The Lunar Crater Observation and Sensing Satellite mission in 2009 deliberately crashed a spent rocket stage into Cabeus Crater, a permanently shadowed crater near the South Pole. The impact threw up a plume of debris that was analyzed by instruments on the following spacecraft. The results confirmed the presence of water ice mixed with the regolith, along with other volatile compounds like carbon monoxide, ammonia, and even small amounts of mercury. The distribution of ice in these cold traps varies. Some craters appear to have relatively high concentrations, perhaps several percent water ice by mass in the upper few inches of regolith. Others show weaker signals, suggesting lower concentrations or ice buried deeper beneath dry regolith. The total amount of water ice in all permanently shadowed regions combined might range from about 100 million to 600 million tons, though this remains uncertain and is an area of active research. We've explored the Moon, as an object, examining its formation, its physical characteristics, its surface features, and the craters that mark its face. Now we can shift our perspective slightly and consider the Moon not in isolation, but in its relationship with Earth. This relationship, primarily gravitational but with far-reaching consequences, defines much of what makes the Moon unique among solar system moons. The Moon orbits Earth at an average distance of 238,855 miles, measured from the center of Earth to the center of the Moon. But this orbit is not circular. It's elliptical, meaning the Moon's distance from Earth varies throughout each orbit. At its closest approach, called perigee, the Moon comes within about 225,623 miles. At its farthest point, called apogee, it recedes to about 251,000 966 miles. This difference of about 26,343 miles represents a variation of approximately 11% in distance. The orbital period, the time it takes the Moon to complete one orbit around Earth, is 27.32166 days. This is called a sidereal month, measured relative to the distant stars. However, because Earth is also moving around the Sun, the Moon takes slightly longer to return to the same phase as seen from Earth. This longer period, called a synodic month, is 29.53059 days, the familiar interval between full moons. The Moon's orbit is tilted about 5.145 degrees relative to Earth's orbital plane around the Sun. This tilt is why we don't have eclipses every month. Solar eclipses can only occur when the Moon passes between Earth and the Sun, and lunar eclipses can only occur when Earth's shadow falls on the Moon. But because of the orbital tilt, the Moon usually passes above or below the line between Earth and Sun, missing the opportunity for an eclipse. Eclipses only occur when the Moon happens to be near one of the 2 points where its orbit crosses Earth's orbital plane, and when this crossing coincides with a new moon for solar eclipses or a full moon for lunar eclipses. The Moon is tidally locked to Earth, meaning it rotates on its axis in exactly the same time it takes to orbit Earth. This synchronous rotation results in the same hemisphere always facing Earth. The process that created this lock happened gradually over hundreds of millions of years. Earth's gravity creates tidal bulges in the Moon, just as the Moon creates tidal bulges on Earth. When the Moon rotated faster than it orbited, these bulges didn't align with the Earth-Moon line. The misalignment created a torque that slowed the Moon's rotation. Eventually, the rotation slowed to match the orbital period exactly, at which point the bulges aligned perfectly and the torque disappeared. The Moon has remained locked in this configuration ever since. This tidal locking means we always see approximately 59% of the Moon's surface from Earth, not just 50%. The extra 9% comes from libration, apparent wobbling caused by several factors. The Moon's orbit is elliptical, so it moves faster when closer to Earth and slower when farther away, but its rotation rate remains constant. This causes a slight side-to-side rocking called libration in longitude. The Moon's rotation axis is tilted slightly relative to its orbital plane, causing an up and down rocking called libration in latitude. Finally, because we observe from Earth's surface rather than its center, our changing position as Earth rotates provides slightly different viewing angles throughout each day, called diurnal libration. All these effects combined mean that while 50% of the Moon is visible at any given time, different portions become visible over time, allowing us to see 59% total. The remaining 41% of the Moon remained unseen by human eyes until the space age. The Soviet Luna 3 probe photographed the far side in 1959, revealing a landscape dramatically different from the near side. As mentioned earlier, the far side has almost no maria, just heavily cratered highlands. Scientists still debate why this asymmetry exists. One possibility involves the Moon's early history when it orbited much closer to Earth. Earth's strong gravitational field might have affected how the lunar crust formed or prevented lava from reaching the surface on the near side as easily as it did on the far side. Another possibility relates to the Moon's internal structure. Seismic data from the Apollo missions suggests the crust is thicker on the far side, which would make it harder for lava to break through and reach the surface. The Moon is gradually moving away from Earth. The rate is about 1.48 inches per year, determined by bouncing laser beams off retroreflectors that Apollo astronauts placed on the lunar surface. This recession happens because of tidal interactions. The moon's gravity creates tides in Earth's oceans. As Earth rotates beneath these tidal bulges, friction between the water and the ocean floor gradually slows Earth's rotation. This lost rotational energy doesn't disappear. It transfers to the moon, increasing its orbital energy and causing it to spiral slowly outward. The effect is tiny on human timescales, but substantial over geological time. When the moon first formed and orbited much closer to Earth, the tidal forces were enormous. Earth's rotation was much faster, with days lasting only about 6 hours. As the moon moved outward and Earth's rotation slowed, days grew longer. This process continues today. Earth's rotation is slowing by about 1.7 milliseconds per century, and the moon continues its gradual retreat. Extrapolating backward, we can estimate that about 1.5 billion years ago, the moon was about 20,000 miles closer than it is now, and Earth's day was about 18 hours long. Going forward, the moon will continue to recede until, billions of years from now, it reaches a distance where its orbital period matches Earth's rotation period, both locked at about 47 current days. At that point, the same side of Earth would always face the moon, just as the same side of the moon always faces Earth now, and the tidal transfer of energy would cease. However, this will take tens of billions of years, long after the sun has evolved into a red giant and engulfed both Earth and moon. The moon's most obvious influence on Earth is the tides. Tides are primarily caused by the moon's gravity, with the sun contributing about 46% as much tidal force as the moon, despite being vastly more massive, because tidal force depends not on total gravitational pull, but on the difference in gravitational pull across an object's diameter, and the moon is much closer. Understanding tides requires thinking about how gravity works. Every part of Earth is attracted to the moon, but the side of Earth closest to the moon feels a slightly stronger pull than Earth's center, and Earth's center feels a stronger pull than the far side. This difference in gravitational pull across Earth's diameter is what creates tides. On the side of Earth facing the moon, water is pulled slightly away from the solid Earth beneath it, creating a tidal bulge. On the opposite side of Earth, the solid Earth is pulled slightly away from the water, which due to inertia tends to stay where it is, creating another tidal bulge on the far side. These two bulges, one facing the moon and one opposite, remain approximately aligned with the moon as Earth rotates beneath them. As Earth rotates, any given point on the surface passes through both bulges once per day, experiencing 2 high tides and 2 low tides approximately every 24 hours and 50 minutes. The extra 50 minutes accounts for the moon's motion in its orbit. During the time Earth completes one rotation, the moon has moved forward in its orbit about 13 degrees, so Earth has to rotate slightly more than 360 degrees for the same point to realign with the moon. The height of tides varies depending on several factors. When the sun and moon align, either during new moon or full moon, their tidal forces add together, creating spring tides with the highest high tides and the lowest low tides. When the sun and moon are at right angles to each other during first quarter and third quarter moons, their tidal forces partially cancel, creating neap tides with smaller tidal ranges. The moon's distance from Earth also matters. When the moon is at perigee, closest to Earth, its tidal force is about 18% stronger than average. When combined with a new or full moon, this creates especially large spring tides called peregrine spring tides. The distance effect alone can increase tidal ranges by several inches to over a foot in some locations. Geography plays a crucial role in determining actual tide heights at any specific location. In the open ocean, tides are relatively small, typically less than 3 feet, but when tidal bulges enter shallow coastal areas, they can be amplified dramatically. The shape of the coastline, the slope of the sea floor, and the presence of bays or estuaries all affect how high tides rise. The Bay of Fundy in Canada experiences the world's highest tides, with a range exceeding 50 feet during spring tides. In contrast, some enclosed seas like the Mediterranean have tides of only a few inches. The tides don't just affect oceans. The solid Earth also rises and falls in response to the moon's gravity, though by much smaller amounts. The ground beneath your feet moves up and down by about 12 inches twice per day due to earth tides, also called bodily tides. You don't notice this because everything around you, including the reference points you might use to detect motion, is moving together, but sensitive instruments can measure it precisely. The atmosphere experiences tides as well. Atmospheric tides are small, typically causing pressure variations of only about 1 to 2 hectopascals, but they're measurable and contribute to patterns in atmospheric pressure at different times of day and night. Over geological time, tides have had profound effects on Earth. The tidal slowing of Earth's rotation means that days were shorter in the past. Fossil evidence from coral and other organisms that grew in daily or annual cycles confirms this. Coral from 400 million years ago shows growth patterns indicating that Earth's day was only about 21.8 hours long, and there were about 400 days per year. The length of the year hasn't changed significantly, but the number of days per year has decreased as each day has grown longer. Tides also affect the moon, though in different ways. Early in the moon's history, when it still had a molten interior, Earth's gravity created enormous tides in that molten rock, heating it through friction and helping to keep the interior partially molten longer than it would otherwise have remained. Now that the moon has solidified, Earth still creates small tides in the moon's solid body, with the surface rising and falling by about 4 inches. These tides contribute to the moonquakes detected by Apollo seismometers, adding and releasing stress on lunar rocks as the moon flexes slightly during each orbit. The energy dissipated by tides, both on Earth and to a much lesser extent on the moon, comes from orbital energy. This is why the moon is slowly moving away from Earth and why Earth's rotation is gradually slowing. Energy can't be created or destroyed, only transformed. And the tidal friction that heats Earth's ocean floors and stresses rocks on both worlds comes from orbital and rotational energy being converted to heat. The moon produces no light of its own. Every photon we see coming from the moon began its journey at the sun, traveled 93 million miles to the moon, bounced off lunar rocks, and traveled another roughly 250,000 miles to reach our eyes. The phases of the moon result from changing angles in the Sun-Moon-Earth system as the moon orbits Earth. At new moon, the moon lies between Earth and Sun. The side facing us is dark, completely unlit by the sun. The moon is still there, but invisible against the bright sky during the day or lost in darkness at night. A few days later, a thin crescent appears in the western sky shortly after sunset. This is the waxing crescent moon, with just a sliver of the right-hand side illuminated as seen from the northern hemisphere. Each day, the moon moves about 13 degrees eastward in its orbit, causing it to rise about 50 minutes later than the previous day. As it moves, the angle between the sun, moon, and Earth changes, and more of the moon's illuminated face becomes visible from Earth. The crescent grows thicker, becoming a first quarter moon 7.4 days after new moon on average. At first quarter, the moon has traveled 1/4 of the way around Earth, and we see exactly half of the illuminated hemisphere, a configuration sometimes called a half moon. The moon continues to wax, growing fuller through the waxing gibbous phase. Gibbous means more than half, but less than fully illuminated. At 14.8 days after new moon on average, the moon reaches full phase. Now it lies on the opposite side of Earth from the Sun, and we see the entire illuminated hemisphere. The full moon rises in the east just as the sun sets in the west, remains visible all night, and sets in the west as the sun rises in the east. After full moon, the moon begins to wane, with the illuminated portion shrinking day by day. The waning gibbous moon gradually gives way to third quarter moon, also called last quarter, occurring about 22.1 days after new moon. At third quarter, we again see exactly half the illuminated hemisphere, but now it's the left half rather than the right half, as was visible at first quarter. The waning continues through the waning crescent phase, with the illuminated portion shrinking to a thin crescent visible in the eastern sky before sunrise. Finally, the moon returns to new phase, completing the cycle in an average of 29.53 days. The exact length of the cycle varies slightly because the moon's orbit is elliptical. When the moon moves faster in its orbit, near perigee, the phases progress faster. When it moves slower, near apogee, the phases progress more slowly. The variation is typically only a few hours, but careful observers can detect differences in the timing of phases from one cycle to the next. During the crescent phases, you can sometimes see the dark portion of the moon faintly illuminated by a glow called earthshine. This is sunlight that has bounced off Earth, traveled to the moon, reflected off the lunar surface, and returned to Earth. From the moon, Earth would appear as a large disk showing phases opposite to the moon's phases as seen from Earth. When we see a crescent moon, an observer on the moon would see an almost full Earth shining brightly in their sky, providing enough light to dimly illuminate the lunar landscape. This reflected light then returns to Earth, making the dark part of the moon visible. The angle at which sunlight strikes the moon affects what we see on its surface. When the sun is low on the lunar horizon, near the boundary between day and night called the terminator, shadows are long and even small features cast visible shadows. This is the best time to observe lunar topography through a telescope when craters, mountains, and ridges stand out in sharp relief. At full moon, when sunlight strikes the surface nearly head-on from our perspective, shadows disappear and the moon looks flat and washed out despite being at its brightest. The full moon is actually surprisingly bright. It produces an illuminance of about 0.25 lux at Earth's surface, bright enough to cast shadows and allow navigation without artificial light if your eyes are adapted to darkness. For comparison, indoor lighting typically ranges from 100 to 1000 lux, so the full moon provides about 1/400th to 1/4000th the light of typical indoor spaces. Nevertheless, in an environment without light pollution, the full moon provides ample light for human activities. Different full moons throughout the year have traditional names in various cultures. In North America, Native American and colonial names include the wolf moon in January, snow moon in February, worm moon in March, pink moon in April, flower moon in May, strawberry moon in June, buck moon in July, sturgeon moon in August, harvest moon in September, hunter's moon in October, beaver moon in November, and cold moon in December. These names related to seasonal activities and natural phenomena occurring at each time of year. The harvest moon is defined as the full moon closest to the autumnal equinox. Around this time, the angle of the moon's orbit relative to the horizon in northern latitudes is such that the moon rises only slightly later each successive night rather than the usual 50 minutes later. This means there are several consecutive evenings with bright moonlight shortly after sunset, traditionally helpful for farmers working late to bring in harvests. The hunter's moon is the full moon following the harvest moon and exhibits similar properties to a lesser degree. Supermoons occur when full moon coincides with perigee, the moon's closest approach to Earth. At these times, the moon appears about 14% larger in diameter and about 30% brighter than when full moon occurs at apogee. The difference is noticeable if you compare photographs, but difficult to detect by eye alone, since we have no reference for comparison when looking at the moon in the sky. A blue moon has nothing to do with color. The most common modern definition is the second full moon within a single calendar month. Since the lunar cycle is 29.5 days, and most months are 30 or 31 days long, it's possible, though uncommon, for a month to contain 2 full moons. This happens roughly every 2.7 years. An older definition of blue moon refers to the third full moon, in a season that contains 4 full moons rather than the usual 3. The moon occasionally does appear colored in specific circumstances. During a lunar eclipse, when Earth's shadow falls on the moon often appears reddish or orange. This color comes from sunlight passing through Earth's atmosphere and bending into the shadow. Earth's atmosphere scatters blue, light, and transmits red light, the same effect that makes sunsets orange. This reddened light illuminates the moon during totality, creating what's sometimes called a blood moon, though this is simply the normal color of a totally eclipsed moon, not a separate phenomenon. Very rarely, atmospheric conditions on Earth can make the moon appear bluish. Large wildfires or volcanic eruptions can inject particles of specific sizes into the atmosphere that preferentially scatter red light while allowing blue light through. After the Krakatoa volcanic eruption in 1883, observers reported seeing blue moons and even blue suns for nearly 2 years as volcanic particles circled the globe in the upper atmosphere. Such events are rare, making the moon actually appear blue only a few times per century at most. Between 1969 and 1972, 12 humans walked on the moon. 6 Apollo missions successfully landed astronauts on the lunar surface, each spending between about 21 and 75 hours on the moon before returning to Earth. These missions transformed our understanding of the moon from a distant object studied only through telescopes to a world we had touched, sampled, and explored directly. Apollo 11 landed in Mare Tranquillitatis on July 20th, 1969. Neil Armstrong and Buzz Aldrin spent about 2.5 hours outside their spacecraft, collected about 48.5 pounds of lunar samples, deployed scientific instruments, and took photographs. The landing site was chosen for its relatively smooth terrain and lack of large obstacles, a safe location for the first attempt at landing on another world. Apollo 12 landed in Oceanus Procellarum on November 19, 1969, near the Surveyor 3 spacecraft that had landed unmanned 2.5 years earlier. The crew spent about 7.7 hours outside across 2 moonwalks, collected 75 pounds of samples, and demonstrated the ability to make a precision landing, touching down within about 600 feet of their intended target. Apollo 14 landed in the Fra Mauro Highlands in February 1971. This was the site originally planned for Apollo 13, which had suffered an oxygen tank explosion en route to the moon and returned safely without landing. Apollo 14's crew spent about 9.4 hours outside across 2 moonwalks and collected about 94 pounds of samples, including rocks ejected by the impact that formed Cone Crater. Apollo 15 in July 1971 was the first of the extended J missions, with longer stays, more sophisticated equipment, and the first use of the lunar roving vehicle. an electric car that allowed astronauts to travel much farther from their landing site. The mission landed at Hadley Apennine, near a canyon called Hadley Rill, and the Apennine Mountains. The crew spent about 18.5 hours outside across 3 moonwalks, drove about 17.2 miles in the rover, and collected about 170 pounds of samples. They also deployed an extensive scientific instrument package and left a small satellite in lunar orbit to study the moon's environment. Apollo 16 landed in the Descartes Highlands in April 1972. The crew spent about 20.2 hours outside across 3 moonwalks, drove about 16.6 miles, and collected about 209 pounds of samples. The site was chosen to sample what scientists believed might be volcanic rocks in the highlands, though analysis of the returned samples showed they were impact breccias, rocks formed by meteorite impacts rather than volcanism. Apollo 17 in December 1972 was the final Apollo mission. It landed in the Taurus Littrow Valley, a site chosen to sample both ancient highland material and relatively young volcanic deposits. The crew spent about 22.1 hours outside across 3 moonwalks, drove about 22.2 miles, and collected about 243 pounds of samples. One of the astronauts was Harrison Schmitt, a professional geologist and the only scientist to walk on the moon. The mission returned some of the most scientifically valuable samples of the entire Apollo program. In total, the 6 Apollo landing missions returned 842 pounds of lunar rocks, core samples, and regolith. These samples have been studied intensively for over 50 years and continue to yield new insights. They're stored at the Lunar Sample Laboratory Facility at Johnson Space Center in Houston, kept in nitrogen-filled cabinets to protect them from water and oxygen in Earth's atmosphere. Some samples have been distributed to research laboratories around the world, while others remain unopened, preserved for future study with more advanced techniques that don't exist yet. Analysis of Apollo samples revealed numerous facts about the moon. Radiometric dating established the ages of different types of rocks and confirmed that the moon's surface is ancient, with highland rocks typically between 4.2 and 4.5 billion years old, and mare basalts between 3.1 and 3.8 billion years old. Chemical analysis showed that the moon is depleted in volatile elements, substances that evaporate easily, consistent with the moon forming from a hot, violent impact. Isotopic analysis showed that the moon and Earth have remarkably similar compositions in certain isotopic ratios, supporting the giant impact hypothesis over alternative formation theories. The samples also revealed something unexpected: tiny glass beads found throughout the regolith. These beads formed when meteorite impacts melted lunar rock and splashed molten droplets into the vacuum, where they cooled rapidly into perfect spheres of glass. The beads range from microscopic to about a quarter-inch in diameter, come in various colors depending on their composition, and are abundant enough that every scoop of lunar soil contains thousands of them. Apollo astronauts also deployed seismometers, instruments that detected moonquakes and provided information about the moon's internal structure. They left retroreflectors, mirrors designed to reflect laser beams back to Earth, allowing precise measurement of the Earth-Moon distance. They measured the heat flow coming from the moon's interior, finding it much lower than Earth's heat flow, confirming that the moon has cooled more thoroughly than Earth. They deployed magnetometers that measured the weak magnetic fields in lunar rocks. All these instruments operated for years after the astronauts left, transmitting data back to Earth until they were shut down in September 1977 for budgetary reasons. After Apollo, no humans have returned to the moon, though many robotic missions have. The Soviet Union landed 2 robotic rovers, Lunokhod 1 and 2, which explored the surface for months, driving several miles and sending back thousands of photographs. The Soviet lunar program also sent 3 robotic sample return missions that successfully brought back small amounts of lunar soil without human crews. More recently, many nations have sent spacecraft to orbit or impact the moon. Japan's Kaguya mission mapped the moon in high resolution from orbit. China's Chang'e program has successfully landed multiple spacecraft on the moon, including Chang'e 4, which in January 2019 became the first spacecraft to land on the moon's far side. Chang'e 5 returned samples from the moon in 2020, the first lunar sample return since the Soviet Lunar 24 mission in 1976. India's Chandrayaan missions have orbited the moon and confirmed the presence of water ice in permanently shadowed craters. The samples returned by Apollo, and lunar missions remain the only extraterrestrial samples that humans have brought back to Earth and studied in laboratories, if we exclude meteorites that arrived naturally. These samples have been analyzed with techniques including mass spectrometry, electron microscopy, X-ray diffraction, neutron activation analysis, and many others. They've been sectioned, dissolved, melted, and examined at every scale from the atomic to the hand-sized. Despite decades of study, they continue to provide new information as analytical techniques improve and scientists develop new questions to ask about lunar formation and evolution. To say the moon has no atmosphere is essentially correct for practical purposes, but technically, the moon does have an extremely thin exosphere, a collection of atoms and molecules so sparse that they rarely collide with each other. The total mass of the lunar exosphere is estimated at about 22,000 pounds, roughly the mass of a large truck. This mass is spread over the moon's entire surface area of 14,600,000 square miles, resulting in a density so low that individual atoms might travel hundreds of miles before encountering another atom. At the moon's surface, the exosphere has a density of about 100,000 atoms per cubic inch during lunar night, rising to about 1 million atoms per cubic inch during lunar day. For comparison, Earth's atmosphere at sea level contains about 500 million trillion molecules per cubic inch. The lunar exosphere is thus about 10 trillion times less dense than Earth's atmosphere at sea level and about 100,000 times less dense than Earth's atmosphere at the altitude where the International Space Station orbits. The exosphere consists primarily of helium, neon, hydrogen, and argon, with traces of many other elements. The composition varies with time and location. Helium and neon come mainly from the solar wind, the stream of particles flowing out from the sun that constantly bathes the moon's surface. When solar wind particles, mostly protons and electrons with some helium and heavier elements, strike the lunar surface, most get embedded in the regolith, but some bounce back into space, adding to the exosphere. Argon in the lunar exosphere comes from radioactive decay within the moon. Potassium-40, a radioactive isotope, decays into argon-40 over time. This argon, produced in lunar rocks, seeps out through cracks and pores, eventually reaching the surface and entering the exosphere. The process is slow but continuous, and measurements show that the argon concentration varies slightly, possibly indicating regions where outgassing is more active. Sodium and potassium are also present in the exosphere, detected through spectroscopic observations from Earth and spacecraft. These atoms likely come from micrometeorite impacts that vaporize tiny amounts of surface rock, releasing atoms that can be temporarily accelerated away from the surface. The sodium and potassium form an extended cloud around the moon, with some atoms reaching velocities high enough to escape the moon's gravity entirely and enter orbit around the sun. Water molecules have been detected in the lunar exosphere, particularly at higher latitudes and during the lunar morning when sunlight first strikes the surface. The source of these water molecules isn't entirely certain. Some might come from solar wind protons striking the surface and combining with oxygen atoms in lunar minerals to form water or hydroxyl molecules. Some might be released from the permanently shadowed craters that contain water ice when occasional sunlight strikes during favorable conditions. Some might come from comets that impact the moon, though this is thought to be a minor contribution. The exosphere's density varies dramatically between day and night. During the lunar day, solar radiation heats the surface, giving atoms more energy to escape into the exosphere. Some atoms gain enough energy to escape the moon's gravity entirely, lost to space. At night, without solar heating, atoms settle back to the surface, adsorbing onto cold regolith grains. The exosphere essentially collapses, only to reform when sunlight returns. This day-night cycle creates a migration of volatiles from the day side to the night side. Atoms released on the day side bounce across the surface in ballistic trajectories, each bounce carrying them forward until they land in shadow where they freeze onto the regolith. Over many cycles, this process can transport materials toward the poles, where permanently shadowed regions act as cold traps, potentially concentrating volatiles that would otherwise be lost to space. The moon's lack of a substantial atmosphere has profound consequences. Without atmospheric pressure, liquids can't exist on the surface. Any water exposed to sunlight would immediately sublimate, going directly from ice to vapor. Without atmospheric protection, the surface is bombarded constantly by micrometeorites, particles too small to survive passage through Earth's atmosphere, but large enough to sandblast the lunar surface. Without an atmosphere to moderate temperatures, surface conditions swing from extremely hot to extremely cold. Without an atmosphere to scatter light, the lunar sky is always black, even in daytime, with stars visible even when the sun is up. The lack of atmosphere also means there's no sound on the moon except what's conducted through solid materials. If you were standing on the lunar surface and a meteorite struck a mile away, you would see the flash of impact, see dust thrown into space, but hear absolutely nothing. The vacuum carries no sound waves. Astronauts communicated via radio, their voices transmitted electronically through their suits, because sound couldn't travel through the vacuum between them even if they were standing side by side. This environment, so different from Earth, challenges our intuitions about how landscapes behave. There's no weathering in the usual sense, no erosion by wind or water. The only processes that modify the surface are impacts, which add craters and mix the regolith, and the gradual darkening of exposed surfaces by solar wind bombardment and cosmic rays. Changes happen, but slowly, measured in millions of years rather than seasons or years. For most of the 20th century, scientists believed the moon was completely dry. The Apollo samples showed no water within the detection limits of the instruments available at the time. Rocks that formed from molten magma contained no hydrated minerals that incorporate water into their crystal structure. The prevailing view was that water, if it had ever been present when the moon formed, had been completely lost during the violent impact that created the moon, or had boiled away from the molten surface in the early days of the moon's existence. This view began to shift in the 1999s. The Clementine spacecraft, which orbited the moon in 1994, detected indications that ice might be present in permanently shadowed craters near the South Pole. The Lunar Prospector mission, which orbited from 1998 to 1999, used a neutron spectrometer to detect hydrogen at both poles, consistent with the presence of water ice buried beneath the surface. These early detections were indirect, inferring the presence of water or hydrogen rather than detecting water molecules directly. Confirmation came from the Lunar Crater Observation and Sensing Satellite mission in 2009. As mentioned earlier, this mission intentionally crashed a rocket stage into Cabeus crater near the South Pole. The impact excavated material from about 10 feet below the surface, throwing it into sunlight where instruments could analyze it. The results were unambiguous. Water ice was present, along with other volatile compounds. Subsequent missions have refined our understanding. The Lunar Reconnaissance Orbiter, in orbit since 2009, has mapped the Moon in extraordinary detail and identified numerous permanently shadowed regions where temperatures are cold enough for ice to remain stable. India's Chandrayaan. One mission detected water molecules and hydroxyl, a molecule consisting of one oxygen and one hydrogen atom, on the surface of sunlit regions, though in very small amounts, approximately 10 to 1,000 parts per million. The water ice in permanently shadowed craters appears to be relatively pure in some locations, but mixed with regolith in others. The concentration varies from perhaps 1 to 30% by mass in the upper few inches of soil. The ice likely originates from multiple sources. Some may have been delivered by comets, which are essentially dirty ice balls. When comets strike the Moon, the ice vaporizes but can later condense in cold traps. Some water might form directly on the lunar surface when protons from the solar wind strike oxygen-bearing minerals, creating hydroxyl or water molecules that migrate to cold regions. Some might be ancient, preserved from the Moon's early history, in pockets that have remained permanently cold for billions of years. The total amount of water in all lunar cold traps is uncertain but significant. Estimates range from 100 million to 600 million tons. For comparison, this is enough water to fill a lake several miles across and dozens of feet deep, though on the Moon it's spread through many separate craters and mixed with regolith rather than pooled in a single body. This discovery has practical implications for future lunar exploration. Water is essential for life support, providing drinking water and oxygen. It can also be split into hydrogen and oxygen, both useful as rocket fuel. Having water resources already on the Moon would dramatically reduce the cost of establishing a sustained human presence, since water wouldn't need to be transported from Earth at enormous expense. Water on the Moon also has scientific importance. The permanently shadowed craters act as time capsules, preserving volatiles that might have been delivered billions of years ago. By studying the isotopic composition of water from different locations, scientists hope to learn about the sources of water in the early solar system and how water was distributed to the inner planets, including Earth. Recent research has also identified small amounts of water in samples that were once thought to be completely dry. Glass beads returned by Apollo missions, when analyzed with modern techniques capable of detecting much smaller concentrations than was possible in the 1970s, show water trapped inside, perhaps incorporated when the beads formed from impact-melted rock. Some volcanic glass beads contain even higher water concentrations, suggesting that the Moon's interior might contain more water than previously believed, perhaps 50 to 100 parts per million in some regions of the mantle. These findings continue to reshape our understanding of lunar water. Rather than being bone dry, the Moon appears to have water in multiple forms and locations, though in concentrations far lower than Earth's oceans or even Earth's driest deserts. The distribution of this water, its origins, and the processes that concentrate it in cold traps remain active areas of research, with new missions planned specifically to study lunar water resources. The discovery of water fundamentally changed how we think about the Moon's potential for supporting human exploration and even habitation. What was once seen as a barren, resource-poor world now appears to contain at least some of the raw materials necessary for sustained activity. This shift in perception, based on careful measurement and analysis rather than speculation, represents one of the most significant developments in lunar science since the Apollo program. The interior of the Moon, hidden from direct observation, has been studied primarily through seismic data from the Apollo missions and through careful analysis of the Moon's gravity field and its response to Earth's tidal forces. These indirect methods have allowed scientists to construct a detailed picture of the Moon's internal layers, from the surface down to the core. The lunar crust, as mentioned earlier, averages about 34 miles thick, but varies from about 12 miles in some areas to over 62 miles in others. The crust is thickest on the far side and thinnest beneath some of the largest impact basins on the near side. This variation probably resulted from the giant impacts that created those basins, which excavated crust and thinned it in those locations, combined with the way the crust originally formed during the magma ocean phase. The crust consists primarily of anorthosite in the highlands, a rock type composed mostly of plagioclase feldspar, and basalt in the Maria, volcanic rock that flowed onto the surface billions of years ago. The boundary between crust and mantle is relatively sharp, marked by an increase in density and a change in composition from feldspar-rich rocks to rocks rich in olivine and pyroxene. Beneath the crust lies the mantle, extending down to a depth of about 868 miles. The upper mantle, from the base of the crust to about 310 miles depth, is relatively rigid. Below that, to about 621 miles depth, lies the middle mantle, which may be partially softened by heat, though not molten. The lower mantle, from about 621 to 868 miles depth, transitions gradually toward the core. The mantle is composed primarily of silicate minerals, olivine, pyroxene, and possibly some garnet at greater depths where pressure is high enough to form this denser mineral. The presence of these minerals is inferred from seismic wave velocities, from the Moon's moment of inertia, which tells us how mass is distributed within the Moon, and from the chemistry of mare basalts, which melted from mantle rock and thus reveal the mantle's composition. The mantle is not entirely solid. Seismic evidence suggests there's a partially molten layer, a zone where temperatures are high enough that a small percentage of the rock has melted, creating pockets of magma between solid crystals. This zone exists at depths between about 621 and 932 miles. The percentage of melt is probably small, perhaps 5 to 30%, enough to affect seismic wave velocities, but not enough to create a completely liquid layer. At the Moon's center lies a small core, first conclusively detected through analysis of seismic data and laser ranging measurements. The core consists of two parts: a solid inner core about 150 miles in radius, and a twin-tuned liquid outer core about 205 miles in radius. The total core radius is thus about 205 miles, or roughly 15% of the Moon's total radius. The core is primarily iron, with some nickel and probably traces of sulfur and carbon. Its small size, relative to the Moon's total size, confirms what the Apollo samples suggested. The Moon is depleted in metallic iron compared to Earth. This depletion is consistent with the giant impact hypothesis, which predicts that most of the iron from the impactor Theia merged with Earth's core, while the Moon formed primarily from the rocky mantles of Earth and Theia. The temperature inside the Moon decreases with depth in the opposite pattern to Earth. Earth's core is the hottest part, with temperatures reaching about 9,000 to 11,000 degrees Fahrenheit. The Moon's interior, having cooled much more than Earth's due to its smaller size and lack of plate tectonics to transport heat efficiently, has temperatures that probably don't exceed about 2,700 degrees Fahrenheit even at the core. The exact temperature profile is uncertain, but models based on the Moon's heat flow and composition suggest the core temperature is relatively cool compared to planetary cores. This cool interior explains why the Moon lacks a significant magnetic field today. A planetary magnetic field requires liquid metal in the core combined with convective motion that generates electric currents through a process called a dynamo. Earth's liquid outer core convects vigorously, driven by heat from the solid inner core and by compositional differences as lighter elements rise and heavier elements sink. This creates the currents that generate Earth's magnetic field. The Moon's small, partially molten core may once have generated a weak magnetic field when it was hotter and convecting more actively. Some of the oldest lunar rocks, particularly those from the highlands, are magnetized at strengths suggesting they cooled in a magnetic field, perhaps 1/100th to 1/10th, the strength of Earth's current field. This ancient field probably existed between about 4.2 and 3.5 billion years ago, then decayed as the core cooled and convection slowed or stopped. The Moon's internal structure tells us about its thermal evolution. Large bodies lose heat more slowly than small bodies because volume increases faster than surface area as size increases. A planet or moon loses heat through its surface, so a larger surface area relative to volume means faster cooling. The Moon, being relatively small, has a high surface area to volume ratio and has cooled efficiently over billions of years. Most of the heat remaining in the Moon's interior today comes from radioactive decay of uranium, thorium, and potassium in the mantle and crust, with less contribution from primordial heat left over from the Moon's formation. The rate of heat loss can be measured directly at the surface. Apollo astronauts deployed heat flow experiments at 2 landing sites, measuring the temperature gradient in the regolith and calculating the heat flow. The measurements showed that heat flows from the Moon's interior at about 21 milliwatts per square meter, about half Earth's average heat flow of about 87 milliwatts per square meter. This lower heat flow reflects the Moon's more thorough cooling and its smaller inventory of heat-producing radioactive elements. Understanding the Moon's interior helps explain its volcanic history. The Mare basalts erupted from depths of perhaps 62 to 186 miles within the mantle, where local concentrations of radioactive elements and possibly tidal heating from Earth created pockets of molten rock. This magma rose through fractures created by the giant impacts that formed the basins, erupting onto the surface and flooding the low-lying regions. The volcanic activity lasted for over 1 billion years, but has now essentially ceased as the interior has cooled to the point where magma generation no longer occurs except possibly in very rare, isolated circumstances. The Moon's moment of inertia, a measure of how mass is distributed within a body, provides another constraint on internal structure. If the Moon were uniform density throughout, its moment of inertia would have a specific value. If density increases toward the center, as expected with a denser core surrounded by a lighter mantle and crust, the moment of inertia is lower. By measuring how the Moon responds to gravitational forces and how its orbit behaves, scientists can calculate its moment of inertia and thus learn about its internal density structure. These measurements confirm that the Moon has a small, dense core and a differentiated interior structure. Gravity measurements from orbiting spacecraft have revealed another aspect of lunar structure. mass concentrations, or mascons, beneath many of the large impact basins. These are regions where the density is higher than surrounding areas, creating a slight increase in gravitational pull. Mascons probably formed when the enormous impacts that created the basins compressed and densified the underlying mantle, and when dense mare basalts later filled the basins. Spacecraft orbiting the Moon must account for these mascons, which can perturb orbits if not properly modeled. Beyond tides, the Moon affects Earth in ways that are subtle but potentially profound over long timescales. The most significant of these is the Moon's stabilizing effect on Earth's axial tilt. Earth's rotation axis is tilted about 23.44 degrees relative to the plane of its orbit around the Sun. This tilt is responsible for Earth's seasons. When the northern hemisphere is tilted toward the Sun, it experiences summer; when tilted away, winter. The southern hemisphere experiences opposite seasons. Without axial tilt, there would be no seasons, and climate would be more uniform from equator to poles, though still colder near the poles due to the low angle of sunlight there. Earth's axial tilt varies over time due to gravitational influences from the Sun, Moon, and other planets. Currently, the tilt varies between about 22.1 and 24.5 degrees over a cycle of about 41,000 years. This variation, called obliquity variation, affects climate by changing the contrast between seasons. When tilt is greater, summers are warmer and winters colder. When tilt is smaller, seasons are more moderate. Computer models of Earth's orbital dynamics show that without the Moon, this variation would be much larger. Earth's tilt could vary between 0 and 85 degrees over periods of hundreds of thousands to millions of years. Such dramatic changes would create extreme climate instability. Periods with high tilt would have extreme seasons and potentially allow ice caps to grow at the equator. Periods with low tilt would have minimal seasonal variation, but could lead to permanent ice caps spreading from the poles toward the equator, as the poles receive less summer sunlight to melt winter ice accumulation. The Moon stabilizes Earth's tilt because its gravitational pull on Earth's equatorial bulge creates a torque that helps maintain the orientation of Earth's rotation axis. This stabilizing effect keeps the tilt variations within the relatively modest range we currently experience. While Earth's climate still varies due to many factors, including obliquity cycles, precession of the equinoxes, variations in Earth's orbital eccentricity, and changes in atmospheric composition, the variations are much less extreme than they would be without the Moon. This stability may have been important for the development of complex life on Earth. Life requires relatively stable environmental conditions over long periods. If Earth's climate swung wildly between extreme states, every few 100,000 years, complex ecosystems might have difficulty developing and persisting. Simple life can endure extreme variations, but complex organisms with specialized adaptations often require more stable conditions. The Moon's presence, by moderating these variations, might have made Earth a more hospitable environment for the evolution of complex life. This idea remains somewhat speculative, since we only have one example of a planet with life, Earth, and cannot directly test what would have happened without the Moon. However, the basic physics is sound. The Moon does stabilize Earth's tilt. This stabilization does reduce long-term climate variations, and stable climate is generally favorable for life. The Moon may also have influenced the evolution of life in more direct ways through tides. Tidal pools, regions that are alternately submerged and exposed as tides rise and fall, create unique environments where early life might have thrived, or where the transition from water to land might have been facilitated. Some researchers have suggested that tidal cycles could have provided useful energy sources or environmental cycles that drove chemical evolution toward life. These ideas are harder to test and remain more speculative than the tilt stabilization effect. The moon's influence on Earth has changed over time as the moon has moved farther away. 4 billion years ago, when the moon was much closer, tides were much larger, potentially hundreds of feet, rather than the few feet typical of open ocean tides today. These enormous tides would have dissipated vast amounts of energy through friction, potentially affecting Earth's early climate and geology. The shorter day length when the moon was closer would also have affected atmospheric circulation patterns and ocean currents. How these differences might have influenced the origin and early evolution of life is unknown but worth considering. As the moon continues to slowly recede, its stabilizing effect on Earth's tilt will gradually weaken, though this process will take hundreds of millions to billions of years to become significant. Eventually, in the very distant future, the moon will be far enough away that its stabilizing influence diminishes, and Earth's axial tilt might begin to vary more dramatically. However, by that time, many billions of years from now, other factors will likely have changed Earth's environment far more profoundly, including the sun's gradual brightening and eventual evolution into a red giant. For all of human history, until the middle of the 20th century, the moon was an object that could only be observed from a distance. Despite this limitation, humans developed extensive knowledge about the moon's motions and phases, knowledge that informed calendars, navigation, and cultural practices worldwide. The lunar cycle of 29.53 days is close to the length of a month in many calendar systems, though not exactly matched. 12 lunar cycles total about 354 days, 11 days short of a solar year. Calendar systems have handled this mismatch in various ways. Some, like the Islamic calendar, follow the lunar cycle strictly, causing the calendar to drift relative to the seasons. Others, like the Hebrew calendar and the traditional Chinese calendar, add an extra month periodically to keep the calendar aligned with both the lunar cycle and the solar year. The Gregorian calendar, used internationally today, abandoned direct connection to lunar cycles in favor of months of arbitrary lengths that keep the calendar synchronized with Earth's orbit around the sun. Ancient astronomers tracked the moon's position against the background stars with remarkable precision. Babylonian astronomers around 2,500 years ago could predict eclipses using careful records of lunar motions. Greek astronomers calculated the moon's distance from Earth using geometric methods, achieving estimates that were surprisingly accurate given their simple instruments. Aristarchus of Samos, around 250 BCE, estimated the moon's distance at about 227,000 miles, remarkably close to the actual average distance of 238,855 miles. The invention of the telescope in the early 17th century transformed lunar observation. Galileo Galilei, observing the moon through his telescope in 1609, saw mountains, valleys, and dark plains, proving that the moon was a world with topography rather than a smooth sphere. He estimated the heights of lunar mountains by measuring the lengths of shadows they cast and found that some were comparable to Earth's tallest mountains. Over the following centuries, astronomers created increasingly detailed maps of the moon. Giovanni Riccioli in 1651 established the naming system for lunar features still used today, assigning names of famous scholars to prominent craters. Johann Maedler and Wilhelm Beer in 1837 published a comprehensive lunar map based on years of careful observation, remaining the standard reference for decades. With the advent of photography in the mid-19th century, lunar mapping became more systematic and accurate, as photographs preserved details that might be missed or misrecorded in drawings. By the mid-20th century, lunar maps were detailed enough to guide spacecraft navigation. The Soviet Union's Luna 3 probe photographed the far side in 1959, revealing the unexpected asymmetry between the near and far hemispheres. Subsequent missions by both the United States and Soviet Union mapped the moon at ever higher resolution, culminating in the Apollo missions where astronauts orbited overhead and walked below, experiencing the landscape directly. The moon has appeared in human mythology and culture across every civilization. Often associated with timekeeping due to its obvious cycle, the moon has been linked to themes of change, cycles, femininity, in many but not all cultures, night, dreams, and mystery. The full moon in particular has been associated with various effects on human behavior, though careful scientific studies have found no correlation between lunar phases and human psychology or behavior beyond what would be expected by chance. The persistence of these beliefs, despite lack of evidence, suggests how powerful the moon's presence in our sky is to human imagination. The moon's surface features have inspired human imagination in ways both fanciful and scientific. The dark Maria, visible to the naked eye, have been seen as the face of a man in the moon in European tradition, as a rabbit in East Asian traditions, or as various other figures in other cultures. These pareidolia, the tendency to see meaningful patterns in random shapes, reflect the human inclination to find familiar forms in ambiguous stimuli. Lunar eclipses have been recorded throughout history, often seen as ominous events. Ancient Chinese astronomers kept careful records of eclipses, sometimes seeing them as celestial dragons devouring the moon. In some traditions, people would make noise during eclipses to scare away the creature threatening the moon. Once the geometry of eclipses was understood, they became valuable tools for navigation and timekeeping, as eclipse predictions required accurate astronomical knowledge and eclipses were visible from large areas simultaneously, allowing synchronization of records from distant locations. The accurate prediction of eclipses marked major advances in astronomical understanding. Thales of Miletus in ancient Greece reportedly predicted a solar eclipse in 585 BCE, though how he achieved this prediction is not certain. Babylonian astronomers developed the Saros cycle, a period of about 18 years, 11 days, and 8 hours after, which eclipses repeat in similar patterns, allowing prediction without full understanding of the underlying geometry. The Antikythera mechanism, an ancient Greek astronomical calculator recovered from a shipwreck and dating to about 100 BCE, could predict solar and lunar eclipses using a complex system of gears. The moon has served as a timekeeper since prehistoric times. The regular cycle of phases provides a natural way to mark time intervals longer than a day but shorter than a year. Many early societies used lunar calendars, where months were defined by the moon's phases and years contained 12 or 13 lunar months. The challenge with purely lunar calendars is their mismatch with seasonal cycles, which depend on Earth's orbit around the Sun. Agricultural societies need to track seasons to know when to plant and harvest, so many developed lunar-solar calendars that incorporated both lunar and solar cycles. These calendars typically added extra months periodically, to keep the calendar aligned with seasons. The Islamic calendar remains a purely lunar calendar, with 12 months of either 29 or 30 days, alternating in a pattern that approximates the lunar cycle as closely as possible. A full cycle of 12 lunar months is about 354 days, causing Islamic months to move through the seasons over a 33-year cycle. Ramadan, the Islamic month of fasting, thus occurs at different times of the solar year in different years. The Hebrew calendar is lunisolar, with months following lunar cycles, but an extra month added in 7 out of every 19 years to keep holidays aligned with seasons. This 19-year cycle, called the Metonic cycle after the Greek astronomer Meton who documented it, is based on the fact that 19 solar years is almost exactly equal to 235 lunar months, making it possible to keep a calendar synchronized with both cycles by adding 7 extra months in. Specific years of the 19-year cycle. The traditional Chinese calendar is also lunisolar, incorporating both lunar months and solar terms that divide the solar year into 24 segments. Chinese New Year falls on the new moon between January 21st and February 20th, ensuring it remains roughly aligned with late winter. In navigation, the moon served as a celestial landmark. The moon's position among the stars changes predictably, moving about 13 degrees eastward each day as it orbits Earth. Navigators could use the moon's position, combined with knowledge of the time, to determine their location, though this required accurate tables predicting the moon's position, which were not available with sufficient precision until the 18th century. The method of lunar distances, measuring the angle between the moon and the sun or specific stars, allowed mariners to determine time and thus longitude at sea. Accurate lunar distance tables were published, beginning in the 1760s, providing an alternative to the newly developed marine chronometers for determining longitude. Lunar distance measurements were tedious and required careful observation, but they worked without relying on mechanical clocks that might fail at sea. The moon also served as an aid to nighttime navigation simply by providing light. A full moon provides enough illumination to travel, read, or work outdoors without artificial light. Armies often planned operations during full moon periods when possible, as the light aided movement without revealing positions as obviously as fires or lamps would. Maritime navigation was easier during full moon periods, when rocks, shores, and other hazards were visible. Modern timekeeping has abandoned lunar cycles in favor of atomic clocks that define the second based on atomic transitions in cesium atoms. However, the month as a time unit, though divorced from lunar phases in modern calendars, preserves the memory of its lunar origin. The word month itself derives from moon, as do similar words in many languages. Beyond craters, which dominate the lunar landscape, the moon displays various other surface features that record its geological history. These features, formed by volcanic, tectonic, and impact processes, add complexity to the lunar landscape and provide insights into processes that shaped the moon billions of years ago. Rilles are channel-like depressions found primarily in the Maria. They come in 3 main types: sinuous rilles, arcuate rilles, and linear rilles. Sinuous rilles meander across the surface like rivers, suggesting they formed through flowing processes. The most likely explanation is that they're collapsed lava tubes. When lava flows from a vent, the surface of the flow cools and solidifies while molten lava continues to flow beneath. If the flow then drains, perhaps because the eruption stopped or the lava drained downhill, it leaves behind a tunnel with a solidified roof. These tunnels can be quite large, sometimes miles wide, and tens or hundreds of feet high. If the roof collapses, either completely or in sections, it creates a sinuous rill following the path of the original lava tube. Hadley Rail, visited by Apollo 15 astronauts, is a prominent sinuous rille about 1 mile wide and perhaps 1,000 feet deep in some places. The rille meanders for about 80 miles across Mare Imbrium. Astronauts drove their rover to the edge of the rill and photographed layered rocks exposed in the walls, providing direct evidence of multiple lava flows that filled the Mare Basin. Arcuate rilles are arc-shaped features, typically concentric with the edges of circular maria. They probably formed as the weight of lava filling an impact basin caused the basin floor to sag, creating concentric fractures and graben. Valleys formed when blocks of crust dropped between parallel faults. Linear rills are straight or gently curved channels, often found in groups of parallel or subparallel features. They're probably graben formed by extension of the crust, stretching and cracking as the moon cooled and contracted, or as loads from lava flows and impacts stress the crust. Wrinkle ridges are another common feature in the Maria. These are low, sinuous ridges, typically hundreds of feet high and miles long, sometimes extending for hundreds of miles. They probably formed when the Maria basalts cooled and contracted, causing the surface to buckle and fold. The compression created folds in the basalt layers, which appear at the surface as wrinkle ridges. The pattern of ridges in different Maria varies, reflecting differences in how those Maria cooled and the stresses acting on them. Domes, as mentioned earlier, are broad, low bumps found in some Maria. They probably formed when viscous lava piled up around a vent rather than flowing away. Some domes have summit pits, small depressions at the top, possibly representing the vent from which lava erupted, or a collapse feature formed after eruptions ceased. Lunar domes are subtle features, best seen when the sun is at a low angle and shadows emphasize small elevation changes. Regolith patterns sometimes show interesting features visible in photographs. Swirl-like patterns of bright and dark material occur in several locations, most famously at Rhina Gamma in Oceanus Procellarum. These swirls correlate with magnetic anomalies, regions where the surface magnetic field is stronger than surrounding areas. The connection between swirls and magnetic anomalies suggests the magnetic fields might protect the surface from solar wind darkening, keeping the bright swirls lighter than surrounding terrain. However, the exact mechanism remains uncertain, and alternative explanations involving unusual surface properties or compositions have been proposed. Some Maria contain ghost craters, crater outlines that are barely visible as slight rises or changes in surface. Tone. These are old craters that were filled to the brim or nearly so by lava flows, leaving only subtle traces visible at the surface. Ghost craters demonstrate that the Maria cover older, heavily cratered terrain that resembles the highlands, but was low-lying enough to be flooded by lava. The Maria also contain irregular depressions and pits that might be skylights, places where the roof of a lava tube collapsed partially, leaving an opening into the underground cavity. Several such pits have been identified in recent years from high-resolution orbital photographs. These features are scientifically interesting because they provide potential access to underground cavities where conditions are more stable than at the surface. Underground, temperature variations are much smaller, and the environment is protected from micrometeorite bombardment and radiation. Such cavities have been proposed as possible sites for future lunar bases, offering natural shelter from the harsh surface environment. Boulders are scattered across the lunar surface, particularly on and around the rims of fresh craters and on steep slopes. Some boulders are enormous, dozens of feet across, thrown out by impacts or exposed by landslides. Boulder fields around recent craters can be dense, with rocks touching or nearly touching each other. Other areas have isolated boulders sitting on otherwise smooth regolith, probably ejected from distant impacts and landing at random locations. The central peaks of complex craters expose rocks from deep beneath the surface, brought up by the rebound that follows a major impact. These peaks provide windows into the moon's structure, revealing materials that would otherwise remain hidden. Analysis of central peak composition from orbital spectroscopy has identified specific minerals and rock types, helping scientists understand what lies beneath different regions. Crater rays, the bright streaks radiating from young craters, consist of material ejected at high velocity during impacts. The brightness comes from fresh material that hasn't been darkened by space weathering. Tycho's rays are the most spectacular, extending across much of the Moon's southern hemisphere, some reaching over 900 miles from the crater. The rays gradually darken over millions of years as the exposed material is modified by micrometeorite impacts and solar wind, eventually fading to match the surrounding terrain. The fact that Tycho's rays remain bright despite the crater being about 108 million years old demonstrates how slowly this darkening process operates in the Moon's airless environment. The Moon's orbit around Earth is more complex than a simple ellipse. The gravitational influences of the Sun and other planets cause subtle perturbations that make the orbit shift and change slightly over time. These variations are small but measurable, and understanding them was essential for predicting the Moon's position, accurately enough to guide spacecraft to lunar landings. The Moon's orbital ellipse slowly rotates in space, a process called apsidal precession. The line connecting perigee and apogee rotates about once every 8.85 years. This means that perigee doesn't occur at the same point in Earth's sky from year to year, but slowly moves through the zodiac constellations over a nearly 9-year cycle. The plane of the Moon's orbit also rotates, a process called nodal precession. The line where the Moon's orbital plane intersects Earth's orbital plane rotates once every 18.6 years. This cycle is important for eclipses, as eclipses can only occur when the Moon is near one of these intersection points, called nodes. The 18.6-year cycle of the nodes corresponds to cycles in eclipse patterns and also to cycles in extreme tides, as the Moon's maximum declination north and south varies over this period. These precession cycles, combined with the Saros cycle and other periodicities, create complex but predictable patterns in the Moon's apparent motion and in eclipse timing. Ancient astronomers recognized some of these patterns empirically without understanding their causes. Modern astronomers can predict the Moon's position to within a few feet at any time in the future using comprehensive models that account for all known perturbations. Libration, the apparent wobbling of the Moon as seen from Earth, comes in several forms. Libration in longitude results from the Moon's varying orbital speed. The Moon moves fastest at perigee and slowest at apogee due to Kepler's second law, which states that objects in elliptical orbits sweep out equal areas in equal times. Because the orbital speed varies but the rotation rate remains constant, we sometimes see slightly more of the eastern limb and sometimes more of the western limb. The maximum libration in longitude is about 7.9 degrees. This may not sound like much, but it's enough to bring features at the edge of the visible hemisphere alternately into and out of view. Some features near the limb are visible only during favorable libration, making them challenging targets for Earth-based observers. Libration in latitude, about 6.7 degrees maximum, results from the Moon's rotation axis being tilted about 1.54 degrees relative to its orbital plane, and the orbital plane being tilted 5.14 degrees relative to Earth's equator. These tilts combine to produce an up and down rocking motion that brings features near the north and south poles alternately into better or worse view. Diurnal libration, up to about 1 degree, results from observing the Moon from Earth's surface rather than its center. As Earth rotates, an observer's position shifts, providing slightly different viewing angles at moonrise versus moonset. This effect is small but real, and for observers seeking to see features right at the edge of the visible hemisphere. Timing observations to take advantage of favorable diurnal libration can make the difference between seeing or not seeing a particular feature. Physical libration, as opposed to the geometric librations described above, involves actual, small wobbles in the moon's rotation. These wobbles result from the moon's imperfect spherical shape and its slightly non-uniform distribution of mass. When the moon rotates, these asymmetries create small torques that cause genuine, though tiny, variations in rotation rate. Physical librations are much smaller than geometric librations, typically less than a few hundredths of a degree, but they're detectable through careful measurement, and they carry information about the moon's internal structure. The moon's smaller size compared to Earth means that the lunar horizon is closer than Earth's horizon. On Earth, the distance to the horizon depends on your height above ground, but for a person of average height, it's about 3 miles. On the Moon, the horizon is only about 1.5 miles away due to the smaller radius of curvature. This closer horizon has practical implications. An astronaut standing on flat terrain on the Moon can see only about 1.5 miles in any direction before the surface curves away out of view. Mountains and crater rims on the horizon appear closer and loom larger than they would on Earth at the same actual distance. The effect contributes to the difficulty Apollo astronauts sometimes had in judging distances, as familiar intuitions developed on Earth don't apply directly to the lunar environment. The black sky, visible even during the lunar day due to the lack of atmospheric scattering, provides no familiar cues for depth perception. Stars are visible during the day, creating a surreal combination of bright sunlight, dark sky, and visible stars that's impossible on Earth, except perhaps from high-altitude aircraft or spacecraft. From the Moon's surface, Earth appears as a disk in the sky, showing phases just as the Moon shows phases when seen from Earth. When Apollo astronauts were on the Moon during the first quarter moon phase, they saw a 3/4 illuminated Earth hanging in their sky. At new moon, when the Moon passes between Earth and Sun, an observer on the Moon would see a full Earth. Earth appears much larger in the Moon's sky than the Moon appears in Earth's sky. With about 4 times the diameter and 16 times the surface area of the Moon's visible disk as seen from Earth, Earth is an impressive presence in the lunar sky. It's also much brighter, reflecting more sunlight due to its larger size, higher reflectivity from clouds and ice, and its atmospheric scattering of light. The full Earth provides more than enough light for an astronaut to work comfortably during the lunar night, casting distinct shadows on the surface. Earth always remains in approximately the same position in the sky as seen from any given point on the near side of the Moon due to tidal locking. An astronaut standing at a particular location would see Earth at a constant altitude and azimuth throughout the lunar day and night, though Earth would rotate once every 24 hours, showing all its continents, oceans, and weather patterns in succession. Earth would also go through phases over the course of a lunar month, from full when the Sun is on the opposite side of the Moon, to new when the Sun is behind Earth from the Moon's perspective. From the lunar far side, Earth would never be visible at all. Astronauts on the far side would see only the black sky, the Sun when it rose, and the unchanging stars. This isolation, cut off from direct sight of Earth and from radio communications with Earth due to the Moon blocking signals, creates a unique environment more remote from human civilization than any other place humans have visited. The experience of seeing Earth from the Moon had profound psychological impacts on Apollo astronauts. Many described the experience as giving them a new perspective on humanity and Earth's fragility. Seeing our entire world as a small, bright disk hanging in the void, all human history and experience confined to that delicate sphere, created what some call the overview effect, a cognitive shift in awareness emphasizing the unity and vulnerability of Earth and its inhabitants. Interest in returning humans to the moon has grown in recent years, driven by scientific goals, technological development, and the potential use of lunar resources. Several nations and private companies are developing plans and capabilities for lunar missions in the coming decade. The scientific case for human return to the moon remains strong. While robotic missions can accomplish many goals more economically, humans offer flexibility, adaptability, and judgment that robots cannot match. A trained geologist on the moon can explore, collect samples, and make observations far more efficiently than even sophisticated robots. The Apollo missions demonstrated this repeatedly, with astronauts making discoveries and collecting critical samples that pre-planned robotic missions likely would have missed. Areas of particular scientific interest include the permanently shadowed craters at the poles, where water ice awaits detailed study. Understanding the amount, distribution, and origin of this ice would shed light on the history of volatiles in the inner solar system. The South Pole Aitken Basin, with its exposure of deep crustal and possibly mantle material, offers insights into the moon's internal structure. The lunar far side, with its different geological history, could reveal why the near and far sides developed so differently. Long-duration human presence on the moon would enable experiments impossible on Earth or in Earth orbit. The moon's low gravity, vacuum environment, and seismic stability make it ideal for certain types of telescopes and scientific instruments. A radio telescope on the far side would be shielded from Earth's radio interference, enabling observations of low-frequency radio emissions from the early universe that are blocked by Earth's ionosphere. Biological experiments in lunar gravity could help us understand how life responds to gravity levels between Earth's and zero gravity. The moon's resources, particularly water ice, could support sustained human presence. Water can be split into hydrogen and oxygen, both useful as rocket propellants. Producing rocket fuel on the moon rather than launching it from Earth would dramatically reduce the cost of lunar operations and of missions departing from lunar orbit to other destinations. The moon could serve as a staging point for missions to Mars or asteroids, with fuel produced locally making such missions more feasible. Lunar regolith contains oxygen bound in minerals. Techniques to extract this oxygen are being developed, as oxygen comprises a large fraction of rocket propellant mass and is also necessary for life support. The regolith also contains metals, silicon, and other elements that could be used for construction and manufacturing. While the technology to use these resources remains largely developmental, the basic feasibility has been demonstrated in laboratory settings. Solar power is abundant on the moon, at least during the lunar day. Some locations near the poles receive nearly continuous sunlight due to the low angle of the sun and the presence of high crater rims and mountains. These peaks of eternal light would be ideal for solar power installations, providing near-constant energy without the need for large battery storage systems to bridge long lunar nights. The economic case for lunar resource utilization remains uncertain. Extracting and using lunar materials would require substantial upfront investment in infrastructure and technology development. Whether this investment could be recovered through reduced launch costs or through the value of lunar products remains debatable. Some propose that the moon's ultimate value might not be in physical resources, but in experience and knowledge. Learning to live and work sustainably on another world, developing technologies that could be applied elsewhere, and expanding human presence beyond Earth as a hedge against existential risks. The moon has served as a natural laboratory for understanding planetary processes. Because the moon preserves its ancient surface better than any other terrestrial body, it provides a window into conditions and processes that operated billions of years ago throughout the inner solar system. The heavily cratered highlands represent the final stages of planet formation, when residual debris from the solar nebula bombarded newly formed worlds. Every terrestrial planet and moon went through this heavy bombardment phase, but only the moon preserves clear, unambiguous evidence of it at its surface. Mars shows some ancient cratered terrain, but wind and possible ancient water have eroded and buried much of the record. Earth's active geology has destroyed all but the very largest and most recent impact structures. The Moon, geologically dead for billions of years, has kept the record intact. The late heavy bombardment, that period of intense impacts about 4 billion years ago, is documented primarily through lunar samples and crater counts. Evidence from those samples suggests that the impact rate increased dramatically for a relatively brief period, then declined. Various theories attempt to explain this spike in impact rate. The most widely accepted involves dynamical evolution of the outer planets, particularly Jupiter and Saturn. As these giant planets migrated slightly in their orbits, they disturbed the asteroid belt and the region beyond Neptune, scattering objects inward toward the inner solar system where they could strike the terrestrial planets and their moons. This bombardment affected all the inner planets. Earth, with a surface area about 13 times larger than the Moon's, would have been struck by even more impactors. Some researchers suggest these late impacts might have delayed the emergence of life on Earth, or might have delivered volatile elements and organic compounds that contributed to life's origin. The evidence comes from the Moon, but the implications extend to Earth and the other terrestrial planets. The Moon's volcanic history provides insights into how small, rocky bodies cool and evolve. The duration of volcanism, from about 3.8 billion years ago to perhaps 1 billion years ago, or even more recently, tells us about the Moon's thermal evolution and the distribution of heat-producing radioactive elements. The composition of mare basalts reveals the composition of the lunar mantle in regions where melting occurred. Differences between basalts from different maria reflect different depths of melting and different mantle source regions, allowing scientists to map chemical variations within the Moon's interior. The Moon's lack of a significant atmosphere makes it an ideal place to study impact processes without atmospheric complications. When an asteroid or comet strikes Earth, the object must first pass through the atmosphere, which can slow it down, heat it up, or even fragment it. On the Moon, objects strike the surface at their full cosmic velocity, producing impacts that depend only on the projectile's size, speed, composition, and angle of approach. By studying lunar craters and comparing them to experimental impacts in laboratories, scientists can develop theories of impact processes that can then be applied to other worlds, including Earth. The Moon also serves as a testbed for space exploration technologies. Because the Moon is only 3 days away from Earth, missions can be planned with the option of relatively quick abort and return in case of problems, unlike missions to Mars, which take months to reach and offer no quick return option. Technologies for landing, surface operations, resource utilization, and life support can be tested on the Moon before being deployed on more distant missions. This approach, sometimes called using the Moon as a stepping stone to Mars, leverages the Moon's proximity to reduce risk and cost while still facing many of the same challenges that would be encountered on more distant worlds. The Moon is not Earth's only natural satellite, depending on how you define satellite. Earth temporarily captures small asteroids into orbit around it from time to time, holding them for months to years before they escape back into orbits around the Sun. These temporary satellites, sometimes called quasi-satellites or mini-moons, are typically only a few feet to a few tens of feet in diameter, far too small and distant to see without large telescopes. One well-studied example is 2006 RH-120, an asteroid about 10 feet in diameter that orbited Earth from about 2006 to 2007 before escaping. During its time as a temporary satellite, it completed 4 orbits around Earth. Another object, 2020 CD3, was captured in 2017 and remained in orbit until May 2020, completing several orbits before escaping. These objects are not truly enclosed orbits, but follow complex paths influenced by both Earth's and the Moon's gravity, in some cases orbiting Earth in highly elliptical or even chaotic trajectories that eventually lead to escape. The discovery of mini-moons is relatively recent, not because they're new, but because they're very faint and difficult to detect. Improved telescopes and automated sky surveys designed to detect potentially hazardous asteroids have led to more discoveries in the past 2 decades. Scientists estimate that at any given time, Earth probably has at least one temporary satellite of at least about 3 feet in diameter, though most remain undiscovered due to their faintness and small size. These objects are interesting for several reasons. They demonstrate that Earth's gravitational influence extends far beyond the Moon's orbit, capable of temporarily capturing objects passing nearby. They also represent a potential resource for future space missions, as small asteroids in Earth orbit could be more accessible than those in orbits around the Sun, requiring less energy to reach and potentially providing materials for construction or study. Some proposals suggest deliberately capturing small asteroids into stable orbits around Earth or the Moon for scientific study or resource utilization, though such missions remain in the planning stages. The Moon itself occasionally acquires temporary companions of its own. Small particles ejected from the lunar surface by meteorite impacts can enter temporary orbits, falling back to the surface after minutes to days. Dust levitated by electrostatic forces might also achieve temporary flight above the surface, though this remains uncertain. Apollo astronauts reported seeing a glow on the horizon before sunrise, possibly caused by sunlight scattering off electrostatically levitated dust, but the observations were ambiguous and the phenomenon has not been confirmed by subsequent missions. Moonlight is simply reflected sunlight, but its properties differ from direct sunlight in subtle ways. The Moon's surface reflects only about 7 to 18% of the sunlight that strikes it, depending on surface composition, with darker Maria reflecting less and brighter Highlands reflecting more. This reflected light is also slightly reddened compared to sunlight, as the Moon absorbs more blue light than red light, similar to but less extreme than the reddening of sunlight at sunset on Earth. The full Moon provides about 400,000 times less light than the Sun. If you were using solar panels to charge a battery, it would take about 400,000 times longer to charge the battery by full moonlight than by direct sunlight. Despite this enormous difference, the full moon provides enough light for many purposes. Humans with dark adapted eyes can read large print, navigate terrain, and perform various tasks by full moonlight alone. The moon's light varies by a factor of more than 10 between new and full moon, not simply because more of the moon's surface is illuminated at full moon, but because of an effect called the opposition surge. When the Sun, Earth, and Moon are aligned, with Earth between the Sun and Moon, we see the Moon fully illuminated from directly behind us relative to the Sun's direction. At this geometry, shadows disappear from our view and the Moon appears disproportionately bright. The effect is caused by a combination of shadow hiding, where particles cast shadows on each other at most angles but not at exact opposition, and coherent backscatter, where light waves traveling into and back out of the regolith interfere constructively at small angles. Because of the opposition surge, the full moon is about 2.5 times brighter than the quarter moon, even though the quarter moon has half as much illuminated area visible. The relationship between phase and brightness is not linear but follows a complex curve that depends on the viewing geometry and surface properties. Moonlight affects various aspects of Earth's environment and ecosystem. Many nocturnal animals use moonlight for navigation and hunting. Some species time their activities by lunar cycles, with increased or decreased activity during bright moon phases depending on whether they're predators taking advantage of the light or prey seeking to avoid detection. Coral reefs synchronize spawning events with lunar phases, releasing eggs and sperm simultaneously a few nights after the full moon, maximizing fertilization success and overwhelming predators with the sheer number of larvae. Some plants show growth responses to moonlight, though these responses are subtle and not as well studied as responses to sunlight. Experiments have found slight increases in growth rates for some species during full moon periods, though whether this results from direct response to moonlight or to other factors that correlate with lunar cycles remains unclear. Human responses to moonlight are primarily psychological and cultural rather than biological. While folklore associates the full moon with various behavioral effects, from increased emergency room visits to increased crime rates to changes in mental health symptoms, careful statistical studies have consistently found no correlation beyond what would be expected by random chance. The persistence of these beliefs probably reflects confirmation bias, where people remember correlations between the full moon and unusual events, while forgetting the many times when either occurred without the other. The moon's future, over timescales of millions to billions of years, is determined by the same physical processes that have shaped its past. The gradual recession from Earth, the slow cooling of its interior, and the continuing accumulation of impact debris. The moon will continue to move away from Earth at about 1.5 inches per year, a rate that may decrease slightly as Earth's rotation continues to slow and tidal forces weaken. In roughly 50 billion years, if no other factors intervened, the moon would reach a distance where its orbital period matched Earth's rotation period, both locked at about 47 current days. At that point, the same side of Earth would always face the moon, just as the same side of the moon now faces Earth, and the tidal transfer of energy would cease. However, this equilibrium state will never be reached. In about 5 billion years, the Sun will exhaust the hydrogen in its core and begin fusing hydrogen in a shell around the core. This change will cause the Sun to expand into a red giant, with its outer layers reaching perhaps as far as Earth's current orbit or beyond. Models of stellar evolution suggest the expanding Sun will engulf Mercury and Venus, and possibly Earth as well. The Moon, orbiting Earth, would share Earth's fate. Even if Earth itself is not engulfed, the increased solar radiation and the drag from the Sun's extended outer atmosphere would alter Earth's orbit and heat the Earth-Moon system to temperatures far above what life could tolerate. The Moon's surface would become molten again, returning to a state similar to its earliest days, but through external heating rather than internal heat from formation. On shorter timescales of thousands to millions of years, the Moon will continue to accumulate craters at the current rate, very slowly modifying its surface. The ray systems of currently young craters will gradually darken and fade, eventually becoming indistinguishable from the background terrain. The regolith will continue to thicken as meteorite impacts grind surface rocks into progressively finer particles. The surface will darken through continued space weathering, though this darkening proceeds so slowly that millions of years are required for noticeable changes. The Moon's interior will continue to cool, though by now so slowly that changes over millions of years are insignificant. The core is probably already solid or nearly so, and the mantle has cooled below the point where partial melting is likely. Moonquakes will continue, driven by tidal stresses from Earth and by thermal contraction as residual heat slowly dissipates, but no new volcanic activity is expected. Human activity might alter the moon more significantly than natural processes over the coming centuries. If lunar bases are established, they will leave permanent marks: landing pads, habitats, excavations, roads, and possibly industrial facilities. Robotic and human missions will continue to add artifacts, from scientific instruments to spent rocket stages to various debris. These human modifications, unlike Earth, where erosion and biological processes would eventually erase them, will persist for millions of years, protected by the airless environment and geological stillness. The footprints left by Apollo astronauts in 1969 through 1972 remain essentially unchanged today, 50-plus years later, and will likely remain visible for millions of years, barring the unlikely chance that a meteorite happens to strike precisely where they are. Future lunar archaeologists, whether human or some other species, could study these sites as windows into early space exploration, much as we study ancient human sites on Earth. We've traveled together through the moon's history, from its violent birth in a planetary collision through its volcanic youth to its current state of quiet, slow evolution. We've examined its structure from the deep interior where a small iron core sits silent and cool through the mantle that once generated lava flows but now remains solid and still to the ancient crust scarred by billions of years of impacts. We've explored its surface features, from the towering walls of the largest craters to the fine dust that preserves footprints for eons. We've considered the moon's influence on Earth, the tides it raises, the stabilization it provides to Earth's axial tilt, the light it reflects during our nights. We've traced the history of human observation and exploration, from ancient astronomers tracking its motion with the naked eye, through the Apollo astronauts who walked upon it and brought pieces back for study. We've looked at what the moon has taught us about planetary formation, impact processes, and the history of the inner solar system. Throughout all of this, the moon itself continues its steady orbit, rising and setting, waxing and waning, moving gradually outward but still dominating our nights when it's present. The same face watches Earth as it has for billions of years since tidal locking synchronized its rotation. The same ancient craters mark its surface, bearing witness to events that occurred when Earth was young, and life, if it existed at all, was simple and confined to the oceans. The moon asks nothing of us. It neither knows nor cares whether we observe it, study it, visit it, or ignore it entirely. It will continue on its path regardless of human action, following the mathematical certainties of gravitational physics and thermodynamics. Yet, we continue to look at it, to wonder about it, to find meaning and beauty in its presence. Every human who has ever lived has seen the moon, when weather permitted, and has incorporated it into their understanding of the world and their place within it. For you tonight, the moon simply exists, as it always has. It might be visible in your sky now, or it might be on the far side of Earth, temporarily absent but certain to return. Its light, if you can see. It traveled 93 million miles from the sun, bounced off ancient rocks that have witnessed the entire history of life on Earth, and traveled another 250,000 miles to reach your eyes. The photons that enter your eyes left the sun about 8.3 minutes ago and left the moon about 1.3 seconds ago. They carry no information beyond their wavelength and direction, but they connect you, however briefly and impersonally, to that distant world. Perhaps you'll sleep more easily knowing these facts, these measured certainties about the moon's mass and distance, its composition and history. Perhaps the moon's ancient patience, its slow orbit, its gradual cooling, its eternal preservation of its own past, will encourage your own patience and rest. The moon is not hurrying anywhere. It will be there tomorrow and the next day, and for billions of tomorrows after that, continuing its watchful orbit, reflecting sunlight into Earth's nights, generating tides in our oceans, standing as a constant reminder that worlds exist beyond our own, close enough to visit but far enough to require serious effort and commitment. If you've stayed with me through this long exploration, thank you. I hope you found something of interest, something that sparked curiosity or wonder, or at least something that helped the time pass peacefully. The moon deserves our attention, not because it demands it, but because it rewards it. Every detail we learn reveals new questions, new connections, new appreciation for the complex processes that shape worlds and the fortunate circumstances that placed us on a world with such a prominent, accessible companion. If you found this journey through lunar science and history interesting, if you'd like to explore other aspects of our universe in this same patient, detailed way, please consider liking this video and subscribing to Nebula Nights. There are countless other topics we could explore together, other moons of our solar system, each with its own unique characteristics, planets and their formation, stars and their life cycles, galaxies and the structure they create on the largest scales. The universe is vast and ancient and filled with phenomena worth understanding, worth contemplating quietly as you rest or as you simply take time to think. Until next time, rest well. The moon will be there when you wake, following its eternal path through the sky, patient and constant, asking nothing, offering its reflected light to anyone who looks up. Good night.